Today we're going to turn our attention to free body diagrams. Drawing free body diagrams is an essential part of solving equilibrium problems. While an object is in a given environment, it interacts with other objects around it, exerting forces on those objects and having forces exerted upon it. A free body diagram simply isolates an object from its environment or system and symbolically examines all the forces acting on that particular object. Thus, a free body diagram should be drawn completely isolated from all other objects. We free the body from its system. This allows engineers to focus on the forces acting upon that object. From the free body diagram, engineers can also develop equations which can be used to describe equilibrium, motion, momentum, strength, and many other physical properties. Recall that pushing or pulling on an object is applying force. We represent force as a vector that includes both the direction and magnitude or size of that force. Direction is illustrated by the arrowhead, and the magnitude is illustrated by the length of the line segment, and this is the amount of push or pull. Also recall what a moment is. A moment is that twisting effort about a point or axis when a force is applied at a given distance. To represent a moment, we use an arc with an arrowhead acting about a point, indicating the type of direction, whether that direction is counterclockwise or clockwise. Recall that in order to calculate a moment, you need to have both the force and the perpendicular distance. The force applied is called the line of action, and that perpendicular distance is from the force to that point of rotation. Let's take a look at a free body diagram procedure. Here we have a stack of 3 books, each weighing 5 pounds, which is sitting on top of a table. We're going to take a look at the next few slides at how to draw this free body diagram of just the top book. In order to do this, step 1 tells us that we need to sketch the isolated object. So what is the isolated object? It's the top book. Rather than taking the time to draw the object in detail, we can simply just substitute a simple geometric shape, such as a square or circle. For these exercises, the shape we draw is going to be considered dimensionless. So you can see here that I drew the top book using a simple rectangle. Step 2, we're going to go ahead and sketch the applied and norm forces. When an object is in contact with and is supported by a second object, the second object is going to be replaced by a normal force, which will always be perpendicular to the surface of the second object. So now we can go ahead and sketch the applied force and the norm force. The applied force would be the weight of the top book, and the normal force would be the reaction force that's pushing up the book, causing it not to fall. In step 3, we can go ahead and label the objects and the forces. In the rectangle, I listed this was our top book, which was a PLTW digital electronics book. We have the applied force, which is the weight of the textbook, which is 5 pounds. And we have the normal force, which is holding that textbook up at 5 pounds of force as well. Notice that these two forces have to be in balance, which is why the book is not moving. In step 4, we need to label our dimensions. For more complex free body diagrams, like the truss problem you see below, proper dimensioning is required. This would include the length, height, and angles. So let's take a look at another free body diagram practice problem. Here we're asked to create a free body diagram for the sled pictured below. And you can see that we have 2 people sitting on a sled, and that sled is being pulled, and the sled is rubbing against the ground. So all the forces acting on the sled include an applied force, which is the person pulling the sled. We have the weight of the 2 people on the sled pushing down. We have that normal force keeping the sled from falling. And we have the force of friction, which is coming into play when the sled is rubbing against the ground as it's being pulled. Let's go ahead and take a look at another free body diagram practice problem. Here we're asked to create a free body diagram for the refrigerator picture below. So we have the refrigerator's weight pushing down. We have a normal force that's keeping that refrigerator from falling, and that's always going to be perpendicular to the surface. We have an applied force of the man pushing that refrigerator up the inclined plane, and as he's pushing that up, the refrigerator is going to be rubbing against the surface of the inclined plane, which is causing a force of friction. As you can see on this slide, free body diagrams are frequently used when solving pulley system problems. It's useful to isolate the parts of a pulley system to discover the relationships between each of the parts. This pulley system consists of an upper fixed pulley, which is supporting block mass 1, and a lower movable pulley. The movable pulley is supporting block mass 2. A single rope or cord connects these pulleys together. Keep in mind that both pulleys are going to be considered massless as well as frictionless. For a free body diagram of mass 1, we would start with a small shape. Two forces are acting on mass 1, the weight of mass 1 and the tension force of the rope. We can also isolate the pulleys. Looking at the lower movable pulley, we can draw a free body diagram. The weight of block mass 2 is pulling down on that pulley. Two strands of the rope are pulling up on the pulley, and each of the strands is exerting a tension force. The tension force in a rope is equal in each free body diagram within the system, since there is a single tension force in the entire rope. As we continue to look at more complex free body diagrams, keep in mind that there's also different types of support reactions that we could use. There could be a cable, rope, or chain, a pin support, a roller support, or even a built-in cantilever. Regardless of the type of support reactions, to aid in completing your free body diagrams, connections are often identified with letters. Anytime we use a cable, rope, or chain, we're going to replace that with a tension force only. Here in this example, we have a weight supported from a cable attached to the ceiling. If I was to draw a free body diagram for this example, we would have the weight of the object pulling downward due to gravity, and we would have a tension force in the cable that's keeping that weight from falling. In this example, you can see we have a sign with the weight W is being hung by two cables as shown. Take a few minutes and pause this video to try drawing the free body diagram of both the sign and the cables. So for our free body diagram, you can see we have the sign with a weight that's pointing downward due to the force of gravity, and we have a tension force at cable A pulling to the left, and we have a tension force in cable B that's being pulled diagonally. On this slide, you can see we have now a pin support. A pin support can resist both vertical and horizontal forces, but they cannot resist moments. This means that a pin support is restrained against translation. Think of a pin support as a door hinge. Hinges allow doors to rotate freely, but they do not allow the door to move in any other way. Your knee joint works much in the same way as a pin connection works. They only allow your legs to bend. A pin support allows a structure to rotate, but it does not allow linear movement. As such, two reaction forces are generated at a pin support, one in the X direction and one in the Y direction. In the study of statics, we assume pin connections to be frictionless. The free body diagram of a pin support includes both the horizontal and vertical reactions. Again, it's important to label these reactionary forces. So the pin support, we will call the reactionary force of pin A in the X direction, as well as the reactionary force of pin A in the Y direction. Lastly, make sure to note that the representation of a pin support is a triangle. Here we have a roller support. Roller supports are able to rotate and move along the surface upon which the roller rests. Roller supports only resist perpendicular forces, and they cannot resist parallel or horizontal forces in moments. This means that the roller support will move freely along the surface without resisting any horizontal force. This type of support is provided at one end of all bridge spans. The reason for providing a roller support at one end of a bridge is to allow contraction or expansion of the bridge deck with respect to the temperature differences in the atmosphere. Again, we would label this a reactionary force at roller A in the Y direction. Also notice that the representation of a roller support is a circle. As you heard in the previous slide, a single pin support is not enough to make a structure stable. One more support must be placed on the structure to prevent rotation. Roller supports are always used at one end of a simply supported structure to minimize potentially destructive forces resulting from thermal expansion and contraction. Roller supports can also be rubber bearings that are designed to allow a small amount of lateral movement. The representation of a roller support includes one reactionary force that is perpendicular to the surface. Therefore, beams and truss bridges are always supported with one pin support and one roller support. Again, this is called a simply supported object. So to kind of summarize the last few slides, Anytime you see a triangle, that represents a pin support, and that's going to be replaced with two reactionary forces, both in the horizontal and vertical directions. And anytime you see a circle, that represents a roller support, which will always have one reactionary force that is perpendicular to the surface. A built-in end cantilever is a beam that is held in place by a fixed support. A cantilever is a structural member with one built-in end and one unsupported end. The fixed support shows the supported object literally built into the supporting surface. An example of a built-in end cantilever would be something like a diving board. Here you can see on the left for the free body diagram, I have a pin support with reactionary forces in both the X and Y direction, and I have a moment for that turning effect caused by the force and its rotation. So to do a summary of the support reactions that we looked at today, anytime there's contact between objects, we're going to replace that with the normal force. Remember, the normal force is the force that's holding the object from falling. Anytime you use a cable, rope, or chain, you're going to replace it with a tension force. Anytime you have a pin support, you're going to replace it with two reactionary forces, one in both the horizontal and vertical directions. With a roller support, we're going to replace it with one reactionary force, and it's always perpendicular to the surface. And finally, with the built-in cantilever, we're going to replace it with a horizontal force, a vertical force, as well as one moment. In the next few days, we're going to continue with our discussions of free body diagrams by extending this knowledge to doing truss calculations for truss bridges. Here you can see we have a truss bridge that's supported with a pin at one end and a roller support at the other. Here I want you to get some practice just drawing a free body diagram for this entire truss bridge. Take a few minutes to try this. Here you can see the free body diagram of this entire truss bridge. Recall that on the left side at joint A, we had a pin support. So we have two reactionary forces, RAX and RAY. We had on the right side at joint C a reactionary force for this roller. We call that RCY. And then we had 500 pounds of force in the downward direction. That was our weight.